Okay, let's get started. So let me just say a quiz starts today. And second of all, since your midterm is like next week, right? Next week, Wednesday, I believe. And you have, what do you call it? You have the review on Monday, I think. Anyone? So I think on Monday, since there's no new content, I'll make discussion into office hours. Yeah. So come with your last, yeah, just so everyone's prepared for the midterm. Okay. So any questions on other than any questions about the quiz or the midterm? So let me share screen. So wrote it all out. Okay. So let's get started. So today we'll go over transpositions and a subset of Sn, and then we'll do some questions on it. Yeah, questions on permutations. So recall like an n cycle. N cycle is of the form, right? A1 to AN. Yeah, so a transposition is a 2-cycle. Yeah. So it's interchangeable. You can call a 2-cycle or a transposition. And the point is every cycle can be written as a product of transpositions. And it's sort of transpositions. And it's sort of enough to do it for disjoint cycles, because you can always make a product of cycles disjoint. So if I have, disjoint cycle A1, A2 to AN, this is actually A1, AN, A1, AN minus 1, all the way to A1, A1, A3, A1, A2. Yeah, so for example, like 1, 2, 3, 4 is 1, 4, 1, 3, 1, 2, right? So you could check, right? If you start off here, where does 1 go? Well, 1 goes to 2, right? Nowhere else. Now where does 2 go? 2 goes to 1, and then 1 goes to 3, right? So, and then the left one does nothing because there's no 3 in it, right? And then you ask yourself, where does 3 go? Well, this one has no 3. Here, 3 goes to 1, and then 1 goes to 4. And then you can check 4. 4 goes back to 1, right? So is everyone clear on this? So you can always write a disjoint cycle as a product of 2 cycles. So, okay. Now we say a permutation is even if it can be expressed by even number of transpositions, expressed as even number of transpositions. And then same for odd, right? Now, there's a sort of well-defined thing we need to check, right? Like, can I express this thing as both even and odd? And there's a theorem that says if sigma is product of even number of transpositions, then any other expression is the same than any other product of transpositions equal to sigma is also even. And then, same for odd, right? So for example, what I mean is the book says it pretty well. Like this is the same as this, right? Like here, you see that like they're the same, but this one's odd and this one's odd. So basically the theorem is saying you can express 1/6 as an even number, right? You can express it as a different odd number, right? Like here there's 3 terms and here there's 1 term, but odd remains odd, even remains even, right? So in our case above, right, the 1, 2, 3, 4 is odd because we express it as an odd number of transpositions. Everyone clear so far? So let AN be the set of even let me just say this. You could think of it as the set of even transpositions. It is this set of even transpositions. In other words, you could think of it as also like, the cycles, the set of cycles that are even. Yeah. So from here,
Matthew, sorry,
yeah.
sorry to interrupt. Could you explain like why we eliminate like 2, 3 circle?
Where?
Oh, I mean like 2, 3 times 1/6 times 2, 3, like that permutation. Like why we don't write 2, 3 there?
No, I'm saying these are equal. Like I'm saying these 2 cycles are equal.
Yeah,
Like
yeah. I was wondering why they're equal because you simply just write like the circle permutation of 1/6.
oh I mean this you can check, right? Like 1, where does 1 go? There's no 1, no 1. So 1 goes to 6. And then where does 6 go? Well, there's no 6, no 6. So 6 goes back to 1. And then you ask where does 2 go? Well, 2 goes to 3, and then there's no 3 here. 3 goes back to 2. So 2 gets fixed, and then you see 3 gets fixed, right? Because 3 goes to 2, and then 2 goes back to 3, right? So this is 1/6.
So when it is fixed, we just don't write it, right?
Yeah, like 1/6. I mean, is the same as like this. All the other numbers are fixed.
Oh, I see.
I mean, like, it's just redundant to write this, right?
Okay, I see. Thank you.
Yeah. Okay. So this actually forms a subgroup of Sn. So recall subgroup means I take the same operation as an Sn, right? And the idea is, even plus even is even. So you see that the set of cycles that can be expressed as an odd number of transpositions, those cannot form a group, right? Because you're not close, right? If I give you an odd cycle and then I compose with an odd cycle, it's possible to get an even cycle, yeah. But here, even and even is always even. So it turns out AN forms a subgroup, and the size of it is n factorial over 2. So, right, so, and also, just to be pedantic, even the identity, right, everything is fixed, right? So it's kind of like what you just asked, everything is fixed, so we don't write it. So it's even because we we express it as zero, nothing. So that is just by convention. Okay. So moving on. So let me just give an example. So like A3 is a subgroup of S3. So we can write what S3, right? S3 has what 1, 3, 1, 2, E, 1, 2, 3, 1, 3, 2, 2, 3. Yeah. So you see that these, sorry, let me put commas. So you see that these are not part of is not part of A3, right? Because they're odd number of transposition. I mean, it's just one transposition, right? It's a 1-2 cycle. This is even, right? Because it's 1, 3, and then 1, 2. This is even because it's 1, 2, and 1, 3, right? I'm using that formula I wrote above right here, right? Right, I can express any disjoint cycle as product of transpositions. So this is even. So you see that A3 is the set E 1, 2, 3, 1, 3, 2. Yeah. Everyone good so far?
Yeah, it's all good.
Okay. So moving on, let's start doing questions then. Yeah. So let's start off easy. Let's do, I don't know, 2A. So 1, 3, 4, 5. 1, 3, 4, 5. What is this? 2, 3, 4. So just to refresh how things go, right? So pick a number. You could pick any number, right? Most people like starting with 1, so let's start with 1. There's no 1 here, but here 1 goes to 3, right? And then you do the same thing, right? Where does 3 go? So 1 goes to 3. 3, well here 3 goes to 4, and then 4 goes to 5, right? So 3 goes to 5. And then you ask, where does 5 go? There's no 5 here. Here 5 goes back to 1, right? So when you go back to 1, you close it, right? And then you pick a number not in here, right? 2. Where does 2 go? So 2 goes to 3. And then 3 goes to 4, right? So 2 goes to 4. And then I'm pretty sure 4 goes back to 2, but let's see. Well, what did I erase? What was it? 3? Okay. So 4 goes to 2, right? And then there's no 2 here, right? So 4 goes to 2. So since 4 goes back to 2, I close it. So note, someone asked this last time. Note this, you can't combine it, right? These are not equal. Yeah, the parenthesis matters. Yeah, do not just combine cycles. like that. That's not how things work.
Okay, can you hear me, Master?
Yeah.
Oh, I want to ask in the second row, you wrote that 3 goes to 4 and 4 goes to 5. I want to know that is why it's not 3 goes to 4 and then 4 goes to 2, because in the second bracket is 2, 3, 4. So why it cannot be 3 goes to 4 and then the 4 I count in the second bracket and 4 goes to 2.
Oh, it's by convention. We read right to left.
Yeah,
This is convention.
3 goes to 4. Oh.
So we always go with the right cycle first, and then the left cycle.
Oh.
Yeah.
Oh, okay. I got it. So in for each bracket, we can only use one step, right? For
I
example,
mean,
yeah.
this this is just a function, right? Is just a shorthand notation for the function that maps 2 to 3, 3 to 4, 4 to 2,
Ah,
and keeps everything fixed.
okay, I got it. Thank you.
Yeah. So 2, 3, 4 is the function f that if you like, there's 5 terms, so it's shorthand for this. So right, 2 goes to 3, 3 goes to 4, 4 goes back to 2, and then 1 gets fixed, 5 gets fixed. Yeah. It's just remember your permutations are like bijective functions, right? So these are just shorthand notation for like a function. Okay. Let's do something harder. Let's do I. Yeah, 1, 2, 3, 4, 5. 2I. 1, 2, 3, 4, 5. 1, 2, 5, 4. 1, 2, 5, 4, -2. Okay, so this is a bit harder, but we can use law of exponents, right? The law of exponents say this is just squared, right? So in other words, this is 1, 2, 3, 4, 5. 1, 2, 5, 4 inverse. 1, 2, 5, 4 inverse. Square means you do the operation twice, right? So question, what is the inverse of a cycle? So any ideas? Yeah. Yeah, you're right. It's exactly what you think, right? If we read forwards, right? The inverse is you read backwards. So it's 4, 5, 2, 1. Yeah. So right, and then so and then here I'm gonna do this a bit faster. Yeah. So start with 1. 1 goes to 2. 2 goes to 1. There's no 1 here. 1 goes to 2. Yeah. Oh, sorry. I don't know why I closed that. So moving on. 2 goes to 1. 1. Oh, no. Sorry. Did I mess up? I hope I didn't mess up. I messed up there. So 1 goes to 4. And then 4 goes to 5. And then where does 5 go? 5 goes to 2. 2 goes. Oh, I don't know why I keep doing that. 2 goes to 1. And then 1 goes to 2. Ooh. I must have done something wrong. Hold on. I think so. 1 goes to 4. 4. Oh, I
Yeah,
think
you
that's where I
messed up.
messed up.
So one goes
Yeah,
to 4, 5, and then
yeah, I messed up.
4 again, and you close.
4 goes to 5. 5 goes to 4. Yeah. Yeah, so tell me if I make a mistake. Yeah. So, and then 4 goes to 5, 5 goes to 2, and then 2 goes to 3, right? And then from here we get, there's no 3 in the first, no 3, no 3, no 3. So 3 goes back to 1, right? And I think 2 goes to 5. So here 2 goes to 1, 1 goes to 4, 4 goes to 5, right? So 2 goes to 5, and I think 5, yeah, 5 should go back to 2, but let's check it. So 5 goes to 2, 2 goes to 1, and then there's no 1 here, and then 1 goes to 2, yeah? So yeah, this is the answer, right? But let me go back to A3. You can see that there's 3 elements here, right? So it's pretty clear the inverse of 1, 2, 3 is either itself or 1, 3, 2. Agree? So it turns out it is 1, 3, 2, right? Because from what we just answered here, let me rewrite it. A3 is if it forms a group, it must have inverse, right? So these two are like inverses, right? So we could check it, right? 1, 2, 3, we use the formula. The inverse is 3, 2, 1, right? Which is the same as 1, 3, 2. You could check this, right? Because here, like, this means 1 goes to 3, 3 goes to 2, 2 goes to 1. Same thing here, right? 1 goes to 3, 3 goes to 2, and then 2 goes to 1. So it's just another way to write it.
Oh, Matthew, could you explain like why you say like the inverse has to include it in A3?
So let me think. So if even compose something is identity, right? Compose the inverse, this is supposed to be the inverse. Then if I do even compose inverse, compose, yes. Oh, this, this is quite simple. So if I write my even cycle as a disjoint cycle, right? So if it's A1 to AN, and there's an even number of these, right? A1, AN minus 1, A1, A2, then the inverse is still even, right? Because it's, I could tell you what it is. It's AN, A1, AN, let me think, AN, A2, all the way to AN. Yeah, I mean, it's the same number. Because your cycle type doesn't change, right?
Oh,
Like,
I mean like why you like connect 1, 2, 3 with 1, 3, 2? I mean like why you made the connection there?
oh, I'm just saying. I mean, if you, I'm saying these are inverses.
Or you just like okay. So
Like,
they're you just want to say that they're inverse?
yeah, I mean A3, right? The claim was AN forms a subgroup, right? Or in
Yeah.
general. So I mean, if you form a subgroup, you must have inverses. So yeah,
Oh, I see.
so
Okay.
like, what's the inverse of this? It's either itself or this one, right?
Okay.
Yeah.
Another quick question is like since it's a group, so it satisfies that a group times its inverse you are equals to identity, right? But how can we show like it is equals to identity?
Uh, just check it, right? So where does 1 go? 1 goes to 3, 3 goes to 1. And then where does 2 go? Oh, sorry, there's a plane. 2 goes to 1, and then 1 goes to 2,
Oh, I
and
see.
then and then 3 goes to 2, and then 2 goes to 3, right? So they get fixed. So this is shorthand for like E. This is your E, right? E fixes everything, right? So because from our notation, E seems to be you just write nothing, right? But we have to write something, so we just write E. So okay. Any questions so far? Okay, let's move on. So again, let's do 3. So 3A is simple, right? 3A is just use the formula, right? One, it's disjoint, right? There's no same number. So 1, 4, 3, 5, 6, right? So 3A, 1, 4, we have to express it as a number of transpositions. So it's 1, 6, 1, 5, 1, 3, 1, 4, right? Using the formula we had. And what else? What did they ask? Sorry, I keep going to the wrong. So identify as even or odd, right? So it should be even, right? Because there's 1, 2, 3, 4. So it's even number of transpositions. So so for the second one, you can do the same thing, right? You can do it as if you like. So for me, what I mean by let's do part C, right? 1, 4, 2, 6. And so here, if it's to express it as an even number of transpositions, you just do the same thing, right? And then this is 1, 2, 1, 4. Right, so this is actually odd. Right, not that hard. So moving on. So let's do 5A, right? Let's consider this set. So 5A. It's the set of sigma in S4 such that sigma of 1 is 3. So what are all the possible terms here? So I must send 1 to 3. This is clear. I must have 1, 3 in everything, right? So the question is, what are all the possible terms here? So you can have, you just have to think about it, right? You can have 1, 3 just by itself. You can have 1, 3, 2, 4, right? 1, 3, 4, 2. 1, 3, 4, 1, 3, 2. Am I missing anything? I think that's it, right? I think that's all. So tell me if I'm missing anything, but I think these are all of it, right? It's S4,
Yeah.
so we only have the number 4. So question, is this a group? Is 5A a group? This is actually a very easy question. So what is the second property of a group? In general, it's hard to check whether something's a group, right? Because it's associativity, inverse identity. But if it's not a group, it's easy, right? You just need to show something doesn't hold, like one of those 3. Yeah, identity. Do you see the identity here? No, right? There's no identity, right? Identity sends 1 to 1, right? Here, you send 1 to 3. It's not possible to have the identity. So this is not a group. It becomes hard if it is a group, but yeah, like part B might be a bit harder. And then part C definitely is not a group because you send 1 to 3. So let's move on. S7. Yes. So something I need you all to know. Question. Given disjoint cycle, A1 to AN, what? Oh, I hate these commas. Okay, so given this cycle, what is the order? Any ideas? So if I keep taking powers of it, when do I get the identity back? Remember, order is the smallest power where you get the identity, right?
Is it n?
Yeah, it's n. Why?
Because when you like split them out, like the product of circle, you all get like n circles to give it back to A1.
Product of circles. So I think the problem with transpositions is these are not disjoint, right? You know, like there's like a 1 everywhere here, right? So it's kind of hard to see what happens, right? But let me ask you, what does A1 go? What does A1, A2? What does the first part, where does A1 go? Yeah, it does A1 go? The first power, right? A1 goes to A2, right? That is not the identity. Now, where does the second power take me? So you will all start seeing this. So you'll see why it's n once I ask you these questions. So here, A1 goes to A2, A2 goes to A3, right? So A1 goes to A3. Are you seeing the pattern? So A1, A2, AN cubed, A1 goes to A4, right? And you know, you could see that after n times, A1 goes back to A1, right? Like, you know, the first time, right? So just keep going left, right? The first time, second time, third time, fourth time, and then n minus 1th time, and then the next time you go back. So let's do an example, right? Like 1, 2, 3, right? 1 goes to 2, right? The first power. 1, 2, 3 squared is 1, 2, 3. 1, 2, 3. Here, 1 goes to 3, right? Because 1 goes to 2 and then 2 goes to 3. And then when you cube it, right, you go back to the original, right? Because 1 goes to 2, 2 goes to 3, and then 3 goes back to 1, right? Does everyone see that? So there's a, how do I say it? There's like a structure to these cycles, right? You know where each one goes. And similarly, if I take the second element, right? Like A1, A2, A3, and the first power, A2 goes to A3, right? And then it's the same idea, right? You just, I'm skipping the commas, but I'll put arrow. So, or, yeah, I don't know how to. So here, A2 goes to A4, right? And then so on and so forth. And then after n times, A2 goes back to A2, right? It's the same idea. each one you're moving a step forward, right? So when you square, you move 2 steps forward and then 3 steps forward. So a disjoint n cycle has order n. So note that this is for disjoint, right? So let me try to find you an example. Like this, right? The one we just calculated, or maybe, what's a good example? Yeah, this one, right? We have 1, 3, 4, 5, 2, 3, 4, right? Let me just copy this. 1, 3, 4, 5, 2, 3, 4. And then this, what was it? That was equal to 1, 3, 5, 2, 4, right? So you see from here, do not think the order, so the product of disjoint cycles, you can show, right? Disjoint cycles have order LCM of the length, right? So this has order 2, right? Order 2. And this has order 3, right? So the order of 1, 3, 5, and 2, 4 is LCM of 3 and 2, which is 6, right? Because remember, it's the fact that disjoint cycles, they commute, right? It's sort of abelian for disjoint cycles. But here, do not think that the order of this is unclear, right? Because it's not disjoint, right? There's a 4 here and a 4 here. So if you want to determine the order of a cycle, you make it disjoint first, and then you compute the LCM, right? So the idea is simple, right? Because if this has order 3, they commute, right? So I need to get the identity, right? But because these two are disjoint, this is the same as if I just swap, right? So in general, like sigma tau is not equal to tau sigma unless sigma tau disjoint. And then same thing, right? I have 1, 3, 5, 2, 4. I can swap this and then swap again, and then I get 1, 3, 5 cubed, and then 2, 4 cubed. But the problem is this is E, this is 2, 4, right? Because 2, 4 squared is identity. It has order 2. So you see, like, you need to go 3 more times. So it's like 2, 4. So what I just calculated was 1, 3, 5, 2, 4 cubed, right? I got 2, 4. So it turns out, if you just keep doing the swapping, it's you can see it's the LCM. But do not do this, yeah. Do not, like, the order of this is not 12. I mean, it's not GCD of 4 and 3. Yeah. You have to make it disjoint first. So when determining the order, make your cycles disjoint and then compute the LCM. Yeah. Everyone clear?
That's good.
Okay. Let's do one more. Call it a day. Oh, right. I forgot. The symmetries. of an n-gon is a subgroup. So you know it forms a group, right? But you don't know it forms a, I mean, you can see it forms a subgroup of Sn, right? So again, if I call this 1, I'll do 3 and then 4. If I rotate, you see that these are just elements of S4, right? So here, if I rotate 90 degrees, I get 2, no, not 2, 1, I believe, right? 1, 2, 3, 4, right? So you can see from here, what is my cycle? 1, where did 1 get mapped to? 1 gets mapped to 4. Where does 4 get mapped to? 4 gets mapped to 3. And then where did 3 get mapped to? 3 got mapped to 2. And then 2 got mapped to 1, right? So this is just the cycle, 1, 4, 3, 2. Yeah, so this is rotate 90 degrees. Right? I mean, and then you can, I think I showed last time there's 8, right? There's 4 rotations and like 4 reflections. But, you know, for example, if I reflect about here, right? I get 1, 4, 2, 3, right? So this is just the cycle given by 1 gets fixed, right? 3 gets fixed, but 2 and 4 get swapped. So this is just the cycle 2, 4, right? So later on, you'll see that we call this group Dn. It's called the dihedral group. He'll probably go over that after the midterm, like more on it. But this is a subgroup of Sn, right? Because every rotation reflection is just moving your vertices, right? And then, so everything is determined by how your vertices move. Okay, let's do one more question. Everyone clear? Okay, so I don't know. What should I do? I remember there were like there was a question about, yeah, let's do 27, yeah? So recall a permutation is a bijective map, right? So so number 27. It's a bijective map. You can think of it as bijective map from a set to itself. Right, you could, that's like the, so what they say is let G be a group and let G in G be an arbitrary element. Consider the map lambda G, which maps G to G, be given by, I send the element A to GA, right? So again, this means the group operation, yeah, whatever the group operation is. So right here, right, number 27, I define lambda G to be, I send A to GA. And now I need to show that this is a permutation, right? So show lambda G. So this will hopefully, you know, make clear what a permutation is, right? So how do I check bijectivity? What are the 2 things I need to check for to show? Huh? What are the 2 things? What does it mean to be bijective, I guess?
Injective and surjective.
Yeah, so let's check surjective, right? Given H in G, I need to find, I'm running out of letters. I'll call A such that lambda GA is H, right? This is clear, right? Because what is A? Let A be G inverse H, right? Then lambda G of G inverse H, right, is G inverse H, which is H, right? This is you just go back, you just work backwards. And then injectivity. Right, so what does injectivity mean? It means if lambda GA is equal to lambda GB, then A equals B, right? So picture-wise, it means no two elements can map to the same element in the range, right? So, and like, this is not injective, yeah, because one gets mapped to one and two gets mapped to one, right? So another way to say that is if they're equal, then they have to be equal in the domain, right? In this case, they're not equal in the domain. One is not two. So let's check this, right? What does this mean? This means GA is GB, right? And then by cancellation property, or if you like, you can multiply. By multiply, I mean group operation, G inverse on both sides. That's pretty much what cancellation means. A equals B, right? By cancellation law of group. Yeah, so it's injective and surjective. So it's a permutation. Yeah. For those who don't know what I'm talking about, it's where is it?
It's section 5 permutation.
Yeah, but what I want to show was basic properties of groups. There we go. I'm using right here, right? Proposition 3.22, right? If BA is CA, then B equals C, and then vice versa. If AB equals AC, then B equals C, right? So I'm using the proposition 3.22. If all of you forgot what cancellation law was. So okay, let's stop here. Any questions? So hopefully we're all good on permutations.
Yeah, I have a question about the midterm. So the midterm will like include all the lectures like since like today.
Yeah, I think he plans on going over maybe Monday. It's review and the AN, like the transposition in AN, because he did he go over permutations yet or?
Yep.
Okay, yeah. Then probably today would be like transpositions and AN, and then Monday's review. So
And another thing is like you post the second homework's grade, but I can't see the grades on it, so I don't know what's going on.
second homework grade. Uh, uh
It's like we received it.
oh,
Even
did you see my comment? You're like the last one, right? ZHU. Yeah, you're probably the last. I couldn't see the PDF for yours. I guess it wouldn't load. I think so. I think I put a comment saying, "Can you like email me the homework this time?"
Oh,
Or
sorry, that's my fault. I will like email you later.
okay, cool. Yeah, I think I left the quiz 1 grade. Oh, is it still hidden? Do you
Yeah,
not?
it's still hidden. It is
Oh
still.
yeah. I'll release it. Yeah, thanks.
Oh, and another thing is about the participation. So the grades for participation is like you will release at the end of the like summer session or like each weeks.
I I think participation. The professor, the professor checks that, right? Or
Oh, I don't know. I thought it's like you. Sorry.
yeah, I think the professor. I think participation is like you have to attend lecture or something. So it's either you attend lecture or like you write like a summary or something like that. I forgot.
Yeah. All right. Yeah,
Yeah.
that's all. Thank you.
Okay. So again, Monday is office hours. So bring with you questions. Okay. Um,
Hi, Matthew.
yeah.
So did you? I can't find your email like at the canvas. I only
Oh,
saw the like professor's email. So could you
yeah.
send me
I'll upload,
through the chat?
but let me just write it here for
Yeah,
today.
thank you.
HC4. You got it or?
Oh, wait a minute. I'll write it down. Sorry.
Oh.
Yeah, it's good. Thank you.
Okay.